All right, this is a discussion on graphing rational functions. And in this discussion, we're going to go through a lot of material concerning asymptotes and stuff like that. So there's some prerequisites for this. Specifically, you have to know what a function is, rational functions, you have to have an idea of what those are. It's pretty important that you know and understand the idea of the domain of a function and a range of a function. I will not be rehashing that. And you kind of reaching way back to way back when. We might do a little bit of long division here. Definitely have some factoring going on and graphing, obviously, since we're going to be graphing rational functions. You should be very familiar with finding the intercepts of a given equation, x or y intercepts, horizontal, vertical, whatever that is, and transformations. You should be pretty good with transformations. Those are shifts and reflections. It just depends on who your instructor is, but often they're shifts. They're called shifts and reflections, and stretches and compressions. And finally, you should have a little bit of experience with the idea of an asymptote, but I'll be defining at least the vertical asymptote in this lecture, maybe even the horizontal asymptote. Even though it's assumed to be prerequisite, I would like to even start with the definition of a rational function. This is just a function of the form p of x over q of x, where p and q are both polynomials. And the idea of a rational function is that it is a ratio of function. So I'll just go ahead and highlight that. That's where the rational comes in. It's a ratio, and in this case, the ratio of polynomials. Now, since that should be review, I'm going to go ahead and just mention real quickly what a vertical asymptote is. And a vertical asymptote is usually very useful when you're graphing a rational function. And essentially, these are vertical lines that your graph can never touch. Or in other words, a vertical line of tendency. Now, I should probably note something here. Vertical asymptotes are often the result of dividing by zero. So it's generally, if you're given a rational function where the denominator can turn into zero, you often have a vertical asymptote. Now, this is not always the case, but often the case. So let's take an example. So let's find the vertical asymptotes and the intercepts of the following function: f of x equals x minus 1 over x squared minus x minus 6. This is a rational function because it's the ratio of polynomials. And we'll start with the, we'll start by factoring actually. So let me go ahead and say that this is the same thing as x minus 1 over x minus 3 times x plus 2. Remember, factoring is definitely a prerequisite for this section. And honestly, whenever I'm given a rational function, a rational equation, anything with a fraction in it, I tend to factor denominators anyway, because, well, at worst is that I'm wasting my time, but more often than not, I'm not wasting my time, and this will help out in the long run. Vertical asymptotes often, as said in the note above, it's often the result of division by zero. So I notice, based upon this rational function, that I cannot divide by 0 when x is 3, nor can x be a negative 2. Or maybe I should have said that I cannot let x be 3 or x equal negative 2. So essentially, you could say x cannot equal 3 and x cannot equal a negative 2. And the reason why is because, well, both of those would cause this denominator to be 0. You're essentially solving that denominator equals 0. Okay. So my vertical asymptotes will occur at those 2 points, or on those 2 lines. So let me write that down. The vertical asymptotes are x equals 3 and x equals negative 2. Notice those are equations. And when you graph those on a coordinate system, Cartesian coordinate system specifically, you'll get vertical lines at x equals 3 and a vertical line at x equals negative 2. Those will be my asymptotes. And the second part of this asks us to find the intercepts. Now, again, I'm not going to review intercepts. You should just know that when you plug in x equals 0, you find the y-intercepts. So we know that the y-intercept is 0, not negative, 0, 1/6. And you should know that to find the x-intercepts, you let the output or the y value equal 0. Interesting thing about letting the output or the y value equal to 0 is that there's no need to worry about the denominator. This is a fraction in an equation. Whenever I have a fraction in an equation, I go ahead and multiply both sides by the LCD. If I do that, you find out immediately, because 0 times anything is just 0, that the left-hand side stays 0 and the right-hand side just becomes x minus 1. So essentially what I'm saying here is that to find the x-intercepts, you let the numerator equal 0. And by the way, this implies that x will equal 1. I don't know why I'm boxing that, because in reality I just would write my intercepts here, x1, 0, and the y-intercepts at 0, 1/6. So I've done everything I needed to do. There are my intercepts. So here's a nice little theorem. By using long division, any rational function given of the form ax plus b over cx plus d, where a, b, and c, and d are just some numbers, can be graphed using transformations of the function f of x equals 1 over x. In other words, the graph of that ax plus b over cx plus d kind of looks like the reciprocal function, the 1 over x function. And this should be somewhat familiar to you from algebra courses. If not, that function looks something like this. Okay? Something like it. I mean, obviously I'm drawing freehand, so it's not the best in the world, but it looks something like that. So that's what this theorem is stating, is that if you have a rational function of this form, linear factor over linear factor, it can be graphed somewhat like this, maybe some shifts in transformations. Let's go ahead and prove this first. So let's suppose that somebody came along and gave us this function r of x is equal to ax plus b over cx plus d. Now, I told you early on that a prerequisite for this section would be long division, and the reason why is because I'm going to use it a little bit here and some examples a little bit later on. So I want to find out what this is equal to, and so how I'm going to do that is to use some long division. I have cx plus d dividing into ax plus b. Now, if you remember long division with polynomials, you usually ask, how many times does cx divide into ax? Well, let's find out. Here's ax. I want to see how many times cx divides into it. You see the x's will cancel, so it divides in that many times. Whatever that number is, it divides in that many times. So that will be this part. So let me see what a over c times this binomial here turns into. A over c times cx. A over c times cx. Well, the c's will cancel and will just become ax. And that's by design, it always should. A over c times d is just going to be ad over c. And I subtract. Remember, long division, you subtract. Now, most of this is kind of gobbledygook. Who cares about it? But what's important here is that the ax's will cancel, and b minus ad over c is just some number. That's all I really care about. It's some number. It's the remainder of this long division. And I want you to realize just that. The proof doesn't really depend upon what that number is. What the proof depends upon is that it is a number, that it's not conveniently 0 or some silliness like that. So that means that if I were to perform long division on this polynomial can be written as a over c, or in other words, some number, plus that remainder over cx plus d. If you don't believe me, you could just take for a simple aside and ask yourself, well, let's do, how many times does 17 go into 35, since that's a nice one. So you sit here and you say, okay, 17 goes into 34 twice. 2 times 17 is 34. Do the subtraction. Notice I'm doing the same math here. And you do subtraction, you get 1. 17 can't go into that. So what that tells me is, if somebody asked me what 35 divided by 17 was, I would say, oh, it's 2. Well, plus that remainder over the 17. So when I'm dividing cx plus d into ax plus b, it's a over c. Well, plus that remainder over that cx plus d. Okay. What's important here is that when you graph this business, take a look at the right-hand side of this equation. The only thing that it really involves an unknown, I know you think a, c, and d are unknown, but there's some numbers somebody gave us. The only thing that has the unknown is the second term. And that second term, that one right there, is of the form number over, like some transformation of x. Well, maybe I should say number times x plus number or whatever. It's basically a transformation of 1 over x. So this is why we're saying that it can be written as a transformation of 1 over x, because here's the vertical shift, right, plus some change on the outside of the function, and then here's the stretch or compression, and likely the c also has some effect on that. And then because we're adding on the inside of this function, it's probably a shift right or left. So we have all the components for all of our stretches, compressions, up and down shifts, left and right shifts. Okay, that's the idea of the proof. Well, it's most of the proof, in fact. So on we go. Let's put this somewhat to use here. Let's go ahead and graph this function, 2 over x minus 3. This will be our kind of our testing graph. Now I always like to start my graphs by just labeling intercepts and fun things like that. So we'll look at the x-intercept. Remember, to find the x-intercept, you let the output become 0. If you do that, you'll find out that if there were an x-intercept, it would occur if 0 were equal to 2. That can't happen. That's not possible, so there is no such thing as an x-intercept for this graph. Y-intercept occurs when x is 0, and that's pretty easy to figure out. That's just going to be a negative 2/3. So I'll go ahead and plot that on here. X equals 0, y equals negative 2/3, somewhere around there. So now that I've gone through and done that, I'm going to go ahead and find the vertical asymptote. And from this point forward, when I do the vertical asymptotes, I will just shorthand the language for vertical asymptote as VA. But the vertical asymptote will occur at x equals 3. That's because, well, if x is equal to 3, I'm dividing by 0. So here at x equals 1, 2, 3, right here, I'll draw a dashed vertical line. It's a good habit to get into that just notes to everybody else in the world that that is the line you cannot cross or you cannot touch. Okay, that's our vertical asymptote, and often you're required to even state the equation of the line. Okay, and now there is such thing as a horizontal asymptote, but horizontal asymptotes, and you should have learned this a long time ago, but I'll mention it here. Horizontal asymptotes, you can actually cross these. So the horizontal asymptote is the end behavior. I'll write that in here, horizontal asymptote. And if you know anything about end behavior, it is just what happens as x gets really large. So as x approaches infinity, or in other words, as x gets huge, well, you can see you'll have 2 over some huge number, like a billion, let's say. Well, 2 over a billion is essentially 0. So y basically goes to 0. And as x approaches negative infinity, well, same thing. Y will approach 0, because the fact is, as x goes to negative infinity, you've got like a negative billion in for x, let's say, or a negative trillion. Lose a few more, whatever. So 2 over such a huge negative number is basically 0. Now, take note on a few things here. So now that I've mentioned, actually now that I've mentioned what the horizontal asymptote is, I'll just put dashed lines there for that as well. But I do want you to note, and sorry that I'm not directly on the axis I'm trying to be, but it just doesn't work. Take note that the equation for the x-axis is y equals 0. That means the heights are all 0 there. Also, you can, for a lot of functions, cross the horizontal asymptote. It is allowable, but some functions just won't, like this one. There's no x-intercept. If there's no x-intercept, I'm never going to touch the x-axis, which is where that horizontal asymptote is. Well, I know I'm going through this point right here at y equals a negative 2/3, x equals 0. So I know that I'm going to be in this quadrant of solution, I'm going to be below the x-axis. Okay, so I'm going to essentially just hug this x-axis because, again, it's the horizontal asymptote, which means as time goes on, as x gets really negative, that curve is going to get really close to that dashed line. It's never going to touch it. Now, in the other direction, this vertical asymptote is going to bend the graph here. It'll never be able to touch it. So it's like magnets, actually. Have you ever tried to put two magnets together? The positives together, they push away. You can imagine that you have a magnet. I'm really bad at drawing. Oh, obviously it's not going to work. So just imagine that you have two magnets and you're trying to push them together. There's an asymptote between them, and as you try to push them together, they push off of each other. They actually never really touch. They just push away from each other, and that's exactly what a vertical asymptote is. It's like a magnet that pushes your curve, not technically the opposite direction, but it makes your curve kind of bend away from it a little bit. Now, the second part of my question, really, or the second thing we need to do is find out what the graph looks like to the right of x equals 3. And we have two places where the graph could possibly be. It could be above the x-axis or below. Well, I happen to know this is going to look like 1 over x, so it'll be up above. But a cool little trick is just to take a test point. Like, so let me say pick a test point. And let's go ahead and pick something like x equals 5, just because, well, there's a big number 5 there, so I'll just do that. You don't have to be exact about it. It's just r of 5 is equal to 2 over 5 minus 3. Oh, that's kind of easy, actually. I picked a good point. I didn't mean to. So when I plug in 5, I have an output of 1. Well, that's kind of convenient. So I'll go ahead and shade that in, 5, 1. And because I know I don't have any x-intercepts, it basically means that my graph on this side of x equals 3 is going to exist totally above the x-axis because I can't cross the x-axis. And here, this vertical asymptote will bend me upwards. So that's the graph of 2 over x minus 3. All you're really doing is finding the intercepts. That helps you kind of determine what quadrant, or not quadrant, that helps you determine kind of how your graphs might look. And you're going to find the vertical and horizontal asymptotes. It's good rules of thumb. So let's try another example here. And this time, you notice that there's a little bit more of some junk on top of this. 3x plus 5 is in the numerator. I'm still going to tackle this the same way. I'm going to find the intercepts. So I'll start by saying that. Find intercepts. So let's see, the x-intercept occurs when y is equal to 0. So that means the output is 0. And in this case, you see, oh, I do have the opportunity for that output to be 0. Subtract 5 divided by 3 implies that x is equal to negative 5/3. So this tells me that the x-intercept occurs at negative 5/3, comma, 0. And then the y-intercept, again, just occurs when the input is 0, when x is 0. And you can see by the equation here, or by the function, when x is 0, you have 5 halves. So here we go. We get 0, 5 halves as our y-intercept. And I'll go ahead and plot those. Now, the rest of this we could still do by finding the vertical and horizontal asymptotes actually pretty easily. Let's go ahead and do that anyway. So vertical asymptote, again, the vertical asymptote occurs when you're dividing by 0, so you know that it occurs at x equals a negative 2. You just don't, basically you're asking when is that denominator 0? Oh, it's 0 when you're at x equals negative 2. So I'll go ahead and dash that in here. And now for the horizontal asymptotes, or asymptote, whichever, it occurs as x gets really, really large. Now, this is where what I was mentioning earlier about the shape of this being kind of like 1 over x. The horizontal asymptote, unless you know a little bit of calculus, it's very difficult to determine the horizontal asymptote. Well, not very difficult. It's just new to you. But let me justify my reasoning in the following statement. If I had 3x plus 5 divided by x plus 2, as long as the x is not 0, that was my cat alarm. Okay. As long as x is non-zero, would you agree that I could divide both top and bottom by x? In other words, that I could just divide, basically that I could multiply both top and bottom of this fraction by 1 over x. If I do that, think about that, I'm only multiplying by the number 1, because 1 over x is just 1. I'm not really changing anything. But if I distribute that 1 over x into both numerator and denominator, you get the following. 3 plus 5 over x. And then on the bottom, you get 1 plus 2 over x. What's nice about this is that if you imagine x getting really, really huge, so as x goes off to infinity, like we're talking like billions, okay, trillions, quadrillions, actually much larger than that. It's really hard to capture the idea of the infinite in this sentence, but the idea is there. The x is huge. Well, 5 over some huge number, this is essentially 0, right? Same thing here. 2 over some huge number. Think about it. 2 over 1,000, that's close enough to 0 for, me, I guess. 2 over a billion, that's even closer to 0. 2 over a trillion, that's even closer to 0. And as x goes to infinity, that billion in the denominator is going to get so huge. Yeah, so those two, as x gets really large, go to 0, and you're just left with 3 plus 0 over 1 plus 0, or in other words, y is going to approach 3. The same argument can be used as x approaches negative infinity. The fact is that you still have large denominators here, so you still have 3 plus 0 over 1 plus 0, so the output is still going to approach 3. So I'm going to go ahead and graph on here the horizontal asymptote so we can see how it's going to tend as time goes on. So there we have it. Notice I've labeled my horizontal and vertical asymptotes on the axis, always a good idea. And then we can graph this. I mean, this is pretty much all you need. Now, I'm going to start on the side where I have some points plotted. The fact that there's a point here and a point here tells me I'm likely going to curve between those 2 points just like this. Also, that I'm likely to bend down this way. Like, in other words, I'll approach this vertical asymptote and kind of skid along it going down to negative infinity. As far as the to the right here, it's just going to approach this horizontal asymptote. It actually might bump above it, but that's for a different course. For now, we'll just pretend as though it approaches it and gets really close to it. But in calculus, you'll be able to determine if it bumps up above that or not and comes back down. But I think that this is a great look for this. It's definitely got all the information that I need. Now, obviously, there's still another half of this graph. So let's go ahead and approach that. The other half of this graph is going to occur, well, let's see, does it occur above or below the horizontal asymptote? Well, the only way you're going to figure it out is to try a test point. So test point. And let's see, we'll plug in x equals a negative 5. Okay, so x equals a negative 5. Just try that one. And so if we do that, we have s of negative 5 is equal to, it looks like negative 15 plus 5, which is negative 10, over negative 5 plus 2, which is a negative 3. All right, so that's 10 thirds. That's about 3 1/3 or something like that. So when I plug in negative 5, I'm up here at 3 1/3, about there. And that kind of tells me right now, since I don't have any other x-intercepts, it would be surprising if I plotted a point down below this horizontal asymptote, because it might convince me to turn down. But the fact is, I would have to go through an x-axis to do that. And I already found all my x-intercepts. They're already labeled. I only have one of them. So there's no way that I'm going to curve down. I'm definitely going to curve up here. And this will likely hug this horizontal asymptote as time goes on. It's a pretty neat process. Again, you just find the intercepts, find the vertical and horizontal asymptotes. The horizontal asymptotes are kind of interesting because it's as x goes off to infinity that you can find these. So I'm not a big fan of methods. They're like recipes in mathematics, and it leads to a lot of memorization. But the fact is, when you're graphing a rational function, sometimes it's just so much easier if you have a list of things that you kind of check off as you graph. So if I give you a rational function, or you're given a rational function, you should factor everything in numerator and denominator and try to cancel like factors. You should also note what you do cancel, because that could lead to, well, not vertical asymptotes, but what we call holes in graphs. So if I have an example like that, I'll mention that. Second thing you should do is find the intercepts. That's what we've been doing all along. Third thing is find the vertical asymptotes. These occur where the denominators are 0. Fourth thing you should do is find the horizontal asymptotes. And I did that one way, which is just letting x get really large. But I'll show you a more, not a rigorous way at all, but just a different way to do it. And the different way to do it will also introduce the idea of being able to find slant asymptotes as well. And finally, you use all this information to graph. So here we go. Let's try some examples. So here we go. Let's graph h of x equals 2x squared minus 4x plus 5 divided by x squared minus 2x plus 1. First thing I'm going to do is factor. Now, as I try to factor that numerator, I find out immediately that there's no two numbers that multiply to 5 such that I can make a combination of like 2x times 5 plus 1 times x that will add to a negative 4. There's no two numbers that I can see. So I'll go ahead and erase this factorization. Sometimes it's just dumb luck we can't factor a numerator. That's okay. So we have this business. But the denominator definitely factors. The denominator factors to x minus 1 times x minus 1. So it's x minus 1 squared. Now that we've done that, let's go ahead and find the intercepts. So let's see, the x-intercept occurs when the y value is 0. So in other words, the numerator is 0. Now, as we said a moment ago, or as I said a moment ago, that numerator doesn't factor. So we'll have to reach into our bag of tricks. You can either use completing the square, or I'm just going to use good old faithful quadratic formula, right? So the opposite of the b value plus or minus the square root of b squared minus 4ac all over twice a. All right. So we get this 4 plus or minus the square root of, that's 16 minus, oh, this is very interesting, 16 minus 40. Yeah. All over 4. Well, I immediately see I don't need to go any further, because the fact is, this is not real. That doesn't mean that it doesn't exist. It just means that it's not a real number. And the x-axis, a lot of people don't discuss this, but the x-axis is reserved only for real numbers. Therefore, we won't have any x-intercepts. And that's a great indication. Like, if it had come out that there were, 4 plus or minus the square root of 3 all over 4, that would be fine. But the fact that we have a square root of a negative number, not so fine, because again the x-axis only is made of real numbers. Okay, great, no x-intercepts. The y-intercept again occurs, let the input equal 0. And this is easier to find just from the original function. If you just imagine everything with an x gone, you get 5 over 1. So I'm going to go ahead and plot those, or should I say that, when x is 0, y is 1. And like I said, there are no x-intercepts, which is telling. That's very important, because that tells us that we will not cross the x-axis. The next easiest part is finding the vertical asymptotes, which is again where the denominators are 0. That occurs at x equals 1. So I'll go ahead and graph that. And again, noting that I was meticulous by stating that x equals 1 is the equation for the vertical asymptote. Now the horizontal asymptote, I promised just a moment ago that I would show you how to find the equation for the horizontal asymptote a different way. The other way you can find the equation for the horizontal asymptote is by long division. And in general, I don't teach it because there's a faster way to do it, but I'll just show you anyway how to find it. It is somewhat interesting, I guess. You know what? Actually, now that I think about it, let's not do long division. And the reason why is it's easier for me to explain it this way. The degree of the numerator on this original function is 2. The degree on the denominator is also 2. Notice the coefficient of this is 1. This means that they kind of, well, they grow at the same rate. And the only thing that really makes a difference as x gets really large are the coefficients of these. So if I were to divide both top and bottom by x squared, so let me just show you 2x squared minus 4x plus 5, and I have denominator of x squared minus 2x plus 1. If I divide both top and bottom by x squared, you'll get 2 minus 4 over x plus 5 over x squared. Denominator, you can do the same thing. Divide everything by x squared, you'll get 1 minus 2 over x plus 1 over x squared. And again, you're allowed to do this because you're dividing everything by x squared, not just the numerator, but the numerator and denominator. And as x goes on to infinity, or as x basically gets super huge, all this stuff here that has x's in the denominator, all that stuff goes to 0. Grab a calculator and try it out. Put in large values of x in for 1 over x squared, and you'll see it's basically 0. So, as x goes to infinity, y goes to 2. And the same thing in the negative x direction. So my horizontal asymptote is y equals 2. So this might be a good time to notice something. Most of mathematics is about pattern recognition. The good thing to note here is that if your degree in the numerator is the same as the degree in the denominator, so in other words, you have a rational function where the highest power on the top is x squared or whatever, and the highest power on the denominator is the same, then the horizontal asymptote is just a ratio of the coefficients, of the lead coefficients of both numerator and denominator. Now, in this case, it's just the 2 over the 1. In fact, let me do an aside just to talk about that before I continue on. So let me write this as an aside. And let's just say we want to find the horizontal asymptote of ... And I'll just write down a few of these things. 3x to the 15th minus x squared plus 1 all over 2x to the 15th minus x plus 40. As x gets really huge, the horizontal asymptote is actually just going to, because the powers are the same here, it's just going to be 3/2. So, and that's basically because the powers of the numerator and denominator are the same, or on the lead terms. If we had something like y equals a negative 2x to the 10th minus x plus 1, let's just pretend, over 15x to the 30th plus x plus 4 or something like that. This is a different scenario because notice the powers are different. Well, let's be honest here. If x is really huge, like a million, what's bigger, a million to the 10th power or a million to the 30th power? That million to the 30th power is much bigger, much bigger. So you basically have, I'm going to put roughly equals, basically have like small number over huge number. Well, take examples like small number like 1 over 10,000. That's roughly 1 or 0. So if you have this situation where the denominator has a larger power than the numerator, the degree of the polynomial in the denominator is larger than the degree of the polynomial in the numerator, then you know that the horizontal asymptote is going to be 0 because that denominator is so huge it's just dragging it down to 0. Okay, so same degrees mean ratios, 3 over 2, ratios of the lead coefficients. Different degrees, well, if the bottom has a larger degree, then it'll just drag it down to 0. Now, the worst case scenario, I think a lot of students really dislike it, is if you have something like this, negative 2x cubed plus x plus 1 over x squared plus 3 or something like that. Notice the degree of the polynomial in the numerator is larger than the degree in the polynomial in the denominator. In this case, if x is really large, well, the numerator is going to take off and the denominator is going to be really small. So this is going to be like some huge number upstairs and a very small number, not too small, but somewhat small, downstairs. This does not mean that there's not an asymptote. It means that we might have what's called a slant asymptote. And if that's the case, then you need long division. So to summarize, same degree, then it's the ratios. On the other hand, a larger degree in the denominator implies the horizontal asymptote is y equals 0 because the larger degree in the denominator drags the values down to 0. If you have a larger degree in the numerator, which is, I wouldn't say is a horrible scenario, it's just interesting, then you have what's called a slant asymptote. And actually, you can have all different kinds of asymptotes. It doesn't have to be just a slant. It could be a curved asymptote, but we'll just say slant from now. All right, so let's go ahead and go back to our example then. In this case, the numerator and denominator have the same degree, so you take the ratio of their lead coefficients, 2 over 1. That will be our horizontal asymptote. And now the rest of this is just basically picking test points and plotting. Well, I happen to know that I have a vertical asymptote here at x equals 1. I could, I suppose, have this curve go down, but I just don't see that happening, especially because of the fact that if the curve went down over here to the right of the y-axis, it would have to cross the x-axis, and we don't have an x-intercept. So I already know it's going to curve up here. And to the left, it's just going to approach the horizontal asymptote. Again, it could be that it'll dip below the horizontal asymptote. It could happen. But unless it's a very special circumstance, it's very difficult to find out when that occurs. Now, on the other side of the vertical asymptote, we have to determine, is it going to be above the x-axis or above the horizontal asymptote or below the horizontal asymptote? Well, that's a pretty easy question to answer, because the fact is, as time goes on, we want it to approach the horizontal asymptote, and the fact is we don't have an x-intercept, so it's got to do something like this. If it didn't, we would be crossing the x-axis. There you go. Kind of an interesting example. Kind of. So let's try a different problem. And in this case, again, we're going to have to factor or try to factor numerator and denominator. Let's see if that numerator factors. Two numbers that multiply to 3 would only be 3 and 1. And two numbers that multiply to 1 are 1 and 1. Oh, this looks like we might just have a winner here. We'll do a negative here and a positive there. Let's see if that works out. 3 times a negative 1 is a negative 3, plus 1 is a negative 2. Yeah, that works out nicely. The denominator will factor 2x times an x. And let's see, two numbers that multiply to 2, be a 2 and a 1. And let's see, we want a positive 3, so we'll make that a positive, and this is negative. Okay. Nothing cancels here, so we're kind of out of luck there. Let's find the X-Intercepts, or X-Intercept, by allowing y to equal 0, or in other words, allowing the numerator to be 0. And this one has very nice X-Intercepts. The X-Intercepts occur when x is a negative 1/3, y is going to be 0. And when x is positive 1, y will be 0. So I'll go ahead and mark those on the graph here. 1, 0, and negative 1/3, 0. Very close to each other. I should have made the graph slightly larger. Oh well. The y-intercepts, again, you just let x be 0. It's easier to do this with the original function because you can see that's just going to be a half. So I'll mark that on there as well. All right there. So we got these 3 points really close to each other here. So let's go ahead and find out what the vertical asymptotes are. We'd be dividing by 0 if x were equal to 1/2. And we'd be dividing by 0 if x were equal to a negative 2. So I'll go ahead and mark those on here. I definitely should have made a larger graph, but oh well. In the horizontal asymptote, let's see. The degree of the numerator is the same as the degree of the denominator. So the horizontal asymptote will be at y equals the ratio of the lead coefficients, or 3/2. So I'll go ahead and draw that in there. And I got to tell you, that's a lot of information on that graph right there. I see already the only candidate, let's start from left to right, the only candidate area for the graph to the left of x equals a negative 2 is this upper region here. I'll tell you why in a moment after I draw this out. Okay. All right, the reason why, let's suppose that it wasn't in this upper region. Instead, let's suppose it's down here. Well, if it were, I'd have to cross the x-axis, and I don't have an x-intercept over here. So I already know it's like that. Now, the next region between x equals a negative 2 and x equals 1/2, I would probably pick a test point. And a good test point in that region looks to be x equals negative 1. So I'll plug in a negative 1 into the graph. And you can either use the original function or you can use these factored forms. They're both basically just as easy. You'll get this 3 plus 2 minus 1 over 2 minus 3 minus 2. So let's see, that's 5, 4 over negative 3, or negative 4/3. Okay. So this tells me that I'm pretty much right about here. So that gives me an idea that I'm going to be coming from downstairs here. Hard to freehand this. Remember, I cannot cross a vertical asymptote, but I definitely can cross a horizontal. Okay, so it'll look like that again because it's crossing the x-axis. It's not going to come back. It has to go through this y-intercept here, which I've drawn kind of poorly. So it's going to look like that, and then finally, to the right of x equals 1/2. My only real choice, I guess I could come from up above and cross through like this, but if I did, so I'm saying I could be doing this, but the fact is that I have a horizontal asymptote that I'm going to tend towards, and the only way to do that is to come back up and like this, and that's not going to happen. I don't have an x-intercept. So the only other way I could possibly do this is to come from below here and come up and approach the horizontal asymptote. It might actually go above the horizontal asymptote and then sneak back down to it, but it's going to look like this. Okay. By the way, you can always check this on your graphing calculator. If you do that, your graph will look essentially like what I've drawn here in a 10 by 10 window. Now let's try something a little bit more interesting. Although it looks essentially the same. We'll go ahead and graph f of x equals x squared plus 3x minus 4 divided by 2x squared plus 8x. The numerator factors into x plus 4 times x minus 1. The denominator, both those terms have a 2x in common, and I'll be left with an x plus 4. And at this point, I can actually cancel those x plus 4s. Now, this is an important point to make. I have to note, and if you read my method about graphing rational functions, I have to note that x cannot equal a negative 4. If x were to be able to equal negative 4 in this original function, I would end up dividing by 0. So nobody would know that, by the way, if I had just handed them x minus 1 over 2x here. If I just hand them that function, they'll think, oh, x could be anything I want. So that's why you have to let them know x can't be a negative 4. It doesn't create a vertical asymptote. It creates a hole in the graph. So let's go ahead and start graphing this. I'll give myself plenty of room for graphing at this point. So the x-intercepts, if there are any, let's see, let the output be 0, and you'll find that that equals x minus 1. Okay, great. So that means that when x is 1, we have an x-intercept. And I'll go ahead and plot that here. And let's go ahead and find the y-intercepts, if there are any. Again, that's found just by letting x become 0. And I could do that in the original function here. If I let x be 0, I've got a problem. I'll have 0, actually I'll have negative 4 over 0, which is undefined. So that tells me immediately there are no y-intercepts. So no y-intercepts at all. And in fact, when I look for vertical asymptotes, I'm looking here, when is that denominator 0? Oh, it's 0 at x equals 0. Aha! So that tells me my vertical asymptote is actually at x equals 0 here. Hard to see when I graph this out. Maybe I'll use a larger chiseled pen so you can kind of see. Well, maybe you still can't see that actually. Okay, but that's x equals 0. And now I want to find the horizontal asymptotes, if there are any. And because the degree of the numerator is the same as the degree of the denominator, I know the horizontal asymptote will occur at y equals the ratio of the lead coefficients, or in other words, 1 over 2. So I'll go ahead and graph that. And from this point, it's just looking for test points, right? Well, one thing I could do is I could, well, reading from left to right, let's go ahead and take care of the stuff to the left of x equals 0. So I'll pick a test point there. Make sure you don't pick the test point x equals negative 4, because remember we said x can't be that. So let's try f of negative 1. That's actually, yeah, let's try f of negative 1. F of negative 1, when you plug that in, you'll get a negative 2 over negative 2, actually, so you get a positive 1. So this tells me it's not going to bow down, because it has, if it did, I'd have to cross the x-axis. So it's going to bow up here. And here it'll probably hug the horizontal asymptote. On the other side, the test point, a good test point to pick, well, you don't really have to pick much of a test point here, but you could like pick f of, we already know what f of 1 is. Let's pick f of 4. When you plug in 4, you'll get 3 over 8, 3/8. That's not that tall, actually. It's right about here. But we kind of knew it was going to look something like that because the fact is, if I had gone from the top down like this, I'd have to bow back up to get to this horizontal asymptote. And the fact is, that would require me to cross the x-axis later on. And I only have one x-intercept, so that's not possible. So I kind of knew that it was going to do this business here. It might go up above the horizontal asymptote for a little bit. Who knows? Now, the one thing I'm not addressing is the fact that x cannot be a -4. So let me address that right now. X can't be a -4 means that when I approach x equals a -4, there's going to be a hole in my graph. And not a vertical asymptote, just a hole. The graph will continue on past that. You wouldn't even notice it if you didn't look for it, if you didn't zoom into it enough. The fact is, it just puts a skip in your function. So when you have when you're dividing by 0, you have an asymptote. But when you've canceled factors that would have caused you to divide by 0, you have a hole in the graph. And for anybody who knows old sayings, now you know an asymptote from a hole in the graph. And if people don't know old sayings, then, well, that wasn't funny. As a final example, I want to introduce this idea of having a slant asymptote. Notice the degree of the numerator is higher than the degree of the denominator. This creates what is known as a slant asymptote. Because they're not the same degree, it will not be a horizontal asymptote. And because the degree of the denominator is not larger than the degree of the numerator, it also will not be a horizontal asymptote on the x-axis. So let's go ahead and see what happens with this. We'll still approach it with the same kind of flair here. We want to find the x-intercept and all that stuff. We still have to factor. I should do that first. So the numerator will factor to x minus 5 times x plus 1. The denominator is still this plain old x minus 3. And the x-intercept, again, let the output be 0. Oh, we have a couple x-intercepts. How nice for us. So this tells me that the x-intercepts are at 5, 0 and -1, 0. I'll go ahead and plot those points right here. 5, 0 is beautifully placed right there, and -1, 0 right there. Gorgeous, gorgeous point. And then the y-intercept means that we let x be 0. So I plug in 0 for x. And again, I would prefer to just look at the original function here because I can just zero out anything with x's. I'll get 5/3. So let me go ahead. Oh, I should probably note that 0, 5/3. I'm rushing. I shouldn't rush, right? So when x is 0, y is 5/3. There we have it. So those are my 3 kind of intercept points. And now I look for the vertical asymptote. Remember, that's when you're dividing by 0, which occurs at x equals a +3. So I'll go ahead and draw that in. And finally, I would say look for the horizontal asymptote, but there aren't any. Because the fact is, for there to be a horizontal asymptote, the degrees of the numerator and denominator either have to match or the denominator has to be higher degree. So how do you find whatever asymptote this is? Long division. That's right, folks, long division. So no horizontal asymptote. We have a slant asymptote. And let's go ahead and perform some long division. So I'll go to the next page to do that. Remember, it's x squared minus 4x minus 5. X squared minus 4x minus 5. And we're dividing by x minus 3. Let me just double check to make sure that's correct. Yes. All right. Well, here we go. How many times does x go in x squared? Well, x times. Let's check that. X times x. Sure, that's x squared. X times a -3. Sure, that's a -3x. This whole group gets subtracted. You have an x squared minus an x squared. Those cancel by design. You have a -4x minus a negative, or in other words, plus 3x. is a negative 1x, and I'll bring down that minus 5. So how many times does x go into a negative 1x? Well, you better believe it, a negative 1 time. Negative 1 times x is a negative x. Negative 1 times a negative 3 is a positive 3. Subtract off this entire group. That's the biggest mistake students make, is they don't subtract the entire group. Negative x plus x, that's gone. Negative 5 minus 3, that becomes a 2. This is my remainder. So what does that mean? Well, it means that x squared minus 4x minus 5 being divided by x minus 3 can also be written as x minus 1 plus the remainder over the divisor. And at this point you might go, well, what do I do with that? The same thing we have been doing, actually. As x gets really huge, well, this junk right here goes to 0. Now this gets really huge over here, but at least I know this junk goes to 0. Because the fact is, it's 2 over some huge, huge number, either positive or negative. So let me just put plus or minus infinity. So essentially what I'm saying is, as x gets big in the positive or negative direction, the graph looks like x minus 1. So let me write that down, actually. The graph tends to this chunk right here, y equals x minus 1, as x approaches plus or minus infinity. Because that remainder just kind of disappears as x gets huge. So we are going to graph y equals x minus 1. Let's go ahead and go back here. Y equals x minus 1 is a diagonal line. In fact, it's just a line with the y-intercept of negative 1 and a slope of 1. So it kind of looks like this. Not kind of, it exactly looks like this. I was tired of taking my time with drawing it. Okay, so that's what it tends towards. Now let's see what happens when I draw the rest of this. I'll still need test points. So on the left side of this vertical asymptote, x equals 3, I already see right now what's going to happen. I only have one x-intercept over here. And the fact is, I have to tend towards this line, towards the asymptote. So I'm going to approach it this way. It'll come up here. It won't come back down, because if I do, if it did this, I'd have to have another x-intercept right there. So it won't do that. It'll just come up and curl up here. The same argument can be used, well, a similar argument can be used for the right side of the vertical asymptote x equals 3, because the right side of it, I know we have an x-intercept at 5. If it were to go like this, well, I suppose it could. I suppose it could do this. The fact is, it would look like this, but the problem is that it needs to come back up here and tend towards the asymptote, and that means we need to hit another x-intercept, which we don't have. So I'm going to take both those away. I'm going to draw out the most logical way, which is that it comes down here, it hugs the vertical asymptote, comes up here and hugs the slant asymptote. And actually, if you graph this on a graphing calculator, this is exactly what it'll look like. All right, so this is a good introduction, at least, to graphing rational functions. Now in calculus, you'll spend quite a bit of time graphing all different kinds of rational functions and finding out when you cross over an asymptote, a horizontal asymptote, and what's the maximum value, all that fun stuff. So you get more and more technical as time goes on. But with the technology that we have right now, we've gone as far as we possibly can.